Hey, in this lecture we will introduce the derived infinity category of an abelian category. The derived infinity category of an abelian category is a refinement of the usual derived category into the world of infinity categories. In particular, you can still think of it as having objects being given by chain complexes and maps as somehow derived morphisms, or rather equivalence classes of maps are derived homomorphisms. But then there's also higher information encoded as well. And we will construct this by first describing an infinity category where morphisms are actually chain homotopy classes, or equivalence classes of morphisms are chain homotopy classes, and then there's higher information related to chain homotopies as well. And then we will introduce the notion of Dwyer-Kahn localizations, which allows you to turn this into the actual derived category by localizing at quasi-isomorphisms. I'm Achim Krause from Mathematics Münster. So today we will, for an abelian category, A, construct an infinity category dA, which will basically be an infinity categorical refinement of the classical derived category. So, more precisely, objects will be given by chain complexes. And this is really the unbounded version of the derived category. So this is just unbounded chain complexes in A. And the morphisms will be such that equivalence classes of morphisms will be the usual derived hom. So in this sense, this is really a refinement of the classical derived category, and we will simply denote it by d of A, since that's like the only version of the derived category that we will be considering. And the construction we will be following is actually the construction of the derived category that Verdier presented in his thesis already, just he didn't do that in the language of infinity categories. He introduced triangulated categories to do so. But we will see that we basically follow the same steps he did, just in this world. So as usual, we write chain A for the category of chain complexes. So this is really the one category of chain complexes, but we will actually consider it as something slightly stronger. Namely, you can see that this is enriched over the category of chain complexes in abelian groups, which we can just write as chain Z, since abelian groups are Z modules. Right, so this is the usual construction that for any two chain complexes, you really have a mapping chain complex between them, which is built in such a way that its H0 is precisely chain homotopy classes of chain maps. And we will generally call categories enriched over chain complexes DG categories. DG stands for differential graded. And we will now see a construction that allows us to turn such a thing into an actual infinity category, very similar to how we previously turned simplicity enriched categories into infinity categories. And in fact, we will see that in this case, we're actually passing through that construction again. So to do so, we will want to turn a chain complex into a simplicial set, and that's precisely what the Dold-Kahn correspondence does for us. So the Dold-Kahn correspondence is an equivalence between categories, namely chain complexes of abelian groups, and more precisely non-negative chain complexes of abelian groups on one hand, and simplicial abelian groups, so functors delta op to abelian groups, on the other hand. And this is really an equivalence of categories, right, of one categories. So to every chain complex we get a simplicial abelian group, and vice versa. But furthermore, this is lax monoidal. And lax monoidal here with respect to the usual tensor product of chain complexes on this hand and the pointwise tensor product on simplicial abelian groups. It can be a little bit confusing. We saw in another lecture, namely the one with the appendix on simplicial commutative rings, that we also have a lax symmetric monoidal structure on the functor in the other direction. It turns out that basically this Dold-Kahn correspondence is lax monoidal in, like the functor in this direction is lax monoidal, the functor in this direction is also lax monoidal, but only one of them is symmetric. So this is really just lax monoidal, not lax symmetric monoidal. So one way to think about, so we will not be making this precise, but one way to think about where this lax monoidal structure comes from is through the Alexander-Whitney diagonal map on the singular chain complex. That's basically how this arises. Let me not make that precise here. Let me just black box this. So if we can turn chain complexes into simplicial abelian groups in a lax monoidal way, then we can form this composite K from the category of all chain complexes through this category of non-negatively graded chain complexes to simplicial abelian groups, and then finally to simplicial sets. And let me tell you what these functors are. So the middle one is the one that we just discussed. This is gamma. The right-hand side one, that's just the forgetful functor. That just forgets from a simplicial abelian group to the underlying set level-wise. So you get a simplicial set. And this functor is almost just forgetting the negative stuff, but in degree 0, it takes cycles. Right, so this is the functor from chain complexes to non-negatively graded chain complexes that has the property that if you apply this to a chain complex, the new chain complex has the same H0. Right, if you just left the degree 0 part the same and just forgot everything below that, that wouldn't happen. So you have to be careful here. This is putting the cycles in degree 0. In positive degrees, it keeps everything, and in negative degrees, it puts 0. And you can check that all these functors are actually lax monoidal, right? We claimed that for gamma over here, but it's also true for this functor and this functor. All of them have lax monoidal structures. And so if you have a DG category right? This is endowed with mapping chain complexes for every two objects and some composition. Then the Lex monoidal structure here allows you to turn this into a simplicially enriched category. Simply by applying K to each of the mapping complexes in order to get mapping spaces, or mapping simplicial sets to be precise. And the Lex monoidal structure gives you a multiplication structure, a composition structure on that. So this really gives you an enriched category. The same objects, but you've applied K to all the mapping complexes. And this has two very nice properties. So one of them is this actually produces not just simplicial sets, but Kahn complexes. And that just comes from the fact that this forgetful functor from simplicial abelian groups to simplicial sets gives you Kahn complexes. And the other nice property is that the Kahn complexes it gives you are somehow very easy to understand in terms of the previous complex. In particular, they have homotopy groups given by the homology groups of the complex you started with, at least the non-negative homology groups. All right, you forget the negative ones. So at least from the perspective of homotopy groups, these are very hands-on. Let me write that down here. So pi n k of a complex is just hn of that complex for n bigger or equal 0. So let's turn that into a definition, what we just said. So for a DG category, so chain complex enriched category, C, we let the DG nerve of C be the homotopy coherent nerve of the simplically enriched category C delta, where C delta is the simplically enriched category obtained from C by applying this functor k to its Hom chain complexes. And from what we said, since this really gave us Kahn complexes, this really gives us an infinity category. And also note that the mapping spaces here, by what we just said, really have pi 0 given by h0 of the mapping complexes. So for an abelian category A, we define K of A as this DG nerve applied to the DG category of chain complexes, right? And by what we just said, the mapping spaces in this infinity category will have pi 0 given by chain homotopy classes of maps, right? So this is somehow already an infinity category where you should think of the objects as chain complexes, morphisms as chain maps, and then equivalence between morphisms as chain homotopies. So this is a nice infinity category. We will see now that it actually has already finite limits and finite colimits without any assumptions on the abelian category A, which is nice. We will see that after I clean the board. So let's try and see step by step what limits and colimits look like. So we want to prove following proposition: K of A has all finite limits and colimits, and by the discussion in the video about limits and about colimits and decomposition, it really suffices to check very specific cases of finite colimits and limits to get full existence. Namely, it suffices to know that we have an initial and a terminal object and that we have push-outs and pullbacks. So let's see that. First of all, the zero complex is actually both the initial and the terminal object. And that simply, so to see that, we simply have to check that mapping spaces out of this guy, this zero object, are contractible, and similarly maps into are contractible to see that it's terminal. So this is clear, right? Map in Ka from 0 to some complex E is really our functor K applied to the chain complex HOM 0E, but that's just the zero complex, and then K, the sequence of functors really just gives us 0, 0, and then the contractible simplicial set, the delta 0. So this is just a single point for every E, and similarly for maps into the zero complex. So this is exactly what it means to have an initial and terminal object. So I guess at this point we really only need push-outs and pullbacks, but maybe to be a little bit more instructive, let's look at coproducts and products first. So for two objects C and D in K of A, we claim the complex C plus D, right? So this really means the direct sum in the category of chain complexes. Remember, objects in here really come from actual chain complexes. Then this we claim is their coproduct. And for that we need to check that map from K of A C plus D to E for any other complex E is actually equivalent to the product C to E cross map E to E. And again, that's something that's clear on the level of the actual Hom complexes. And then we apply this functor k, so in the end it boils down to the fact that that functor k really preserves products. And similarly, this direct sum is also the product. Right, so the fact from abelian categories that we're used to, that somehow finite coproducts agree canonically with finite products, that carries over to this k of A. So that's nice. So finally, let's think about push-outs. And this is a little bit more tricky. So here we've seen somehow the initial object is just the initial object from chain complexes, and some coproduct and product is just what we did in chain complexes. For push-outs, we have to work a little bit harder. So let's take two maps, F and G, out of the same object. We want to see what the push-out of that is. And similarly to what we did for the category of spaces, we will give some explicit construction, namely some kind of double mapping cone, but now in chain complexes. And this can be given as follows. We define a new chain complex C, F, G. The C here stands for cone, as in mapping cone. It's not that C. And so this will be given by one copy of D and one copy of D prime, and then a shifted copy of C. And the differential is built in such a way that the differential of an element D, D prime, C involves the differential on D and the differential on D prime and the differential on C, but then it also involves these terms F of C here and G of C here. So maybe one nice way of thinking about this is that D and D prime really sit in here as subcomplexes. And then there's some kind of cylinder on C that makes F and G homotopic in this, right? So you can check that there's actually a chain homotopy in here coming from this copy of C between these maps F into this guy and G into this guy. And so this is really like an algebraic analog of this double mapping cone that we explicitly wrote down in spaces. And so this leads to a square like this. And so this is a square not in the one category of chain complexes, but in our funny infinity category K of A. And you'll notice these maps, this doesn't commute on the nose. One goes into the D summand, one goes into the D prime summand. So part of the data of this square is also a chain homotopy between these two composites. Right? This is similar to the square that we had for a push-out in the infinity category of spaces, where we had these two disjoint copies with the cylinder in between, and the square that was our model for the push-out square also involved the data of a homotopy. Right? That's just what giving a square in an infinity category means. And so the claim is that this is a push-out, and for that one has to check something, right? One has to check that the diagram in spaces one gets by mapping out of this, and this is now a diagram in spaces also with a homotopy, that this is a pullback square in the infinity category of spaces. So let's not do that here. But for example, as a little reality check, recall that if you take a pullback in the infinity category of spaces, you usually get some long exact sequences on homotopy groups. And for this situation, you get some long exact sequences on homology groups. And this infinity category was built in such a way that the homotopy groups on the mapping spaces are really homology groups of the mapping complexes. Don't know if that helps you, but that's how I like to think about this. Okay, so this defines pushouts, and the claim is that analogously we can also, so similarly, we have a description for pullbacks that looks a bit similar, but somehow the copy of C, or the middle copy is shifted differently. So this finishes the proof that, or the proof sketch, that K of A has all finite limits and colimits by this decomposition trick that we discussed in the video on colimits and decomposition, that somehow if a category has all, or if an infinity category has an initial and terminal object, and it has pushouts and it has pullbacks, then it already has all finite limits and colimits. One specific piece of notation I want to point out at this point, having discussed how pushouts look like, is that one thing that we will consider quite a lot is the special case of a pushout where the object down here, the D prime, is the zero object. And so the data is just a single map together with the map into the zero object. And in that case, we call this pushout the cofiber of the given map F. So this infinity category K of A that we discussed now, that has objects given by chain complexes, and somehow chain homotopic maps are equivalent in there. But this is not quite the derived category, right? Because here we've just identified things which are chain homotopy equivalent. We have not identified complexes which are quasi-isomorphic. So, for example, in K of A, the map from the chain complex, or this is, I guess, K of Z, K of abelian groups, the chain complex, which is just Z in two subsequent degrees, and 0 in all other degrees, and the map is multiplication by 2. This maps to the chain complex, which has just Z mod 2 and 0 in those degrees, and the 0 map, and also 0 everywhere else. So there is a map like this, but there's no map the other way around, right? There's just no non-zero map from this guy over here. So we see that these complexes, although this map is a quasi-isomorphism, meaning an isomorphism on homology groups, it's not yet an equivalence in our category K of Z. And in the derived category, one really wants all maps which are quasi-isomorphisms to be equivalences. So how do we fix that? Well, the idea is that we want to start with this category K of A and then further pass to another category by inverting all the quasi-isomorphisms, by turning them into equivalences. And so this is by a construction called the Dwyer-Kahn localization. So in the world of infinity categories, there's different things one could mean when one talks about localizations of categories. There's also what's called Bausfield localization. And so this very general approach where we turn a set of morphisms into equivalences, this will be called Dwyer-Kahn localization. So to define that, we let C be an infinity category and W in C1 any subset of morphisms. And remember, we typically mean by this that C consists of a large simplicial set, and so this really is just a subset. Everything is large here, and you don't have to, this is, yeah, there's no size issue here. So a functor f from C to another category C prime, to another infinity category C prime, is called a Dwyer-Kahn localization. At this set of morphisms W if the following two things are fulfilled. So first of all, F needs to invert these morphisms W. So in other words, F takes morphisms from W to equivalences in C prime. And the second condition is that C prime is somehow universal among all such categories under C. And we make that precise as follows. So we say that for every D, so for every other infinity category D, the functor from functors from C prime to D to the category of functors from C to D is fully faithful and has essential image the full subcategory which we're going to denote as fun W CD. So it's the full subcategory of the whole functor category, and it's the full subcategory on those functors C to D which take this class or this set of morphisms W to equivalences. Or said differently, it's clear that precomposition with f takes any functor from C prime to D to a functor that lands in here. So we want the functor from fun C prime D to this fun W C D that we get by precomposing with f. We want that to be an equivalence of categories. Right? So in other words, functors out of C prime are the same as functors from C out of, like, from functors out of C prime into any infinity category D are the same as functors from C into D, which have this property that they take W to equivalences. And so you really see how this is a universal property. And so from that, it's not hard to see that even though we wrote a Dwyer-Kahn localization here, it's really well defined up to equivalence if it exists. So we write C adjoint W inverse for such a C prime. And here's an example, kind of the easiest example where something non-trivial happens, which is if you start with C given by delta 1, and you let W be the set just consisting of the non-trivial morphism, by which I mean the single morphism from 0 to 1. Right? That's the only morphism in here that's not yet an equivalence. So we can ask what happens if we now invert our morphism from W. So feel free to think about this for a second. I'll give you a second to pause the video and think about this. All right. So the claim is that this really produces a category which is just equivalent to delta 0. Right? We're saying that the category with one object and just no non-trivial morphisms is just a localization at this morphism. Right? Your first instinct might have been to do something like take this and add another morphism which is inverse and so on. But you can really just take this one. Right? This is saying that if we invert this morphism, then the two objects become equivalent and there's somehow no information left distinguishing them. So let's see how that comes about. Of course, one needs to prove this. So what one needs to do here is we need to check this universal property, right? There's an obvious functor from delta 1 to delta 0, and it does have the property that it sends W to equivalences. So that's fine. But now we need to check this universal property. In other words, we need to check that the functor from delta 0, like from the functor category out of delta 0 to the functor category out of delta 1, namely just the subcategory of those functors which send our 0 to 1 morphism to an equivalence, that this is an equivalence. Right? And we can check that by proving that it's fully faithful and essentially surjective. And so what does this functor do explicitly on objects? It takes an object in D to the diagram that's really just the identity on that object. So to show that it's essentially surjective, we need to show that for every object in here, right? And that's any morphism in D. Like an object in here is just given by a diagram like this, which is an equivalence, right? So this consists of two different objects and an equivalence between them. We need to check that in this functor category, this is equivalent to an object in the image here, and I claim you can write down an equivalence between this and just the identity at D. So I think that's a very good exercise to get a feeling for what's happening here. So I leave that as an exercise to you, the viewer. But I will say a little bit about fully faithfulness. So for fully faithfulness, we need to understand mapping spaces in this functor category. And the claim is that if you take maps from a diagram consisting of a morphism from A to A prime to a diagram consisting of a morphism G from B to B prime, then this can be described as a pullback of spaces where somehow we put map AB down here. So all of this happens in D, right? This is maps in the functor category. This is just maps in D. So here we put maps from A to B, and up here we put maps from A prime to B prime. And then both of them map down to A B prime, this one by pre-composing with F, and this one by post-composing with G. And the claim is that this mapping space can be described by this pullback. Right? This is a pullback in the infinity category of spaces. So let me not prove that, but you should think of this as somehow a map, the space of maps between these two diagrams is precisely the space of all ways to extend this to a square, right? And how do what data do I need to make a square? I need a morphism from A to B, meaning a point in here. I need a morphism from A prime to B prime, meaning a point in here. And then I need some homotopy between the two composites from A to B prime that I can form. So this is going to be a path down in this space. And if you recall how pullbacks in the infinity category of spaces, how we defined them, we gave a model for that. That also involved somehow a space of paths in the lower one, and then some actual pullback. So at least intuitively, this is exactly the data that you need to construct a square between these two morphisms. And now the point is, so this formula is valid for mapping spaces in this functor category in general, but now the point is that in this full subcategory of the functor category, where we just want the morphisms to be equivalences, we will have that F and G are equivalences. So in other words, post-composition with G and pre-composition with F are also going to be equivalences. And so this diagram, all the maps are equivalences, and so the pullback is going to be equivalent to map from A to B, and also to map from A prime to B prime, right? The pullback will yet be another copy of the equivalence class of this object, and all the maps will be equivalences. And so you see that somehow the mapping space here is just the mapping space from A to B. And so in particular, you see from this that this is really fully faithful. All right. So this settles the easiest kind of prototypical example of a localization. And nothing too crazy happens, right? We plug in some very simple category and we get another one. But now the question is, does this even always exist, right? If I start with some complicated category, like, for example, K of A and all the quasi-isomorphisms, why would I expect this to exist? And let's prove it. So the claim is for any infinity category and any set of morphisms W, this localization, this Dwyer-Kahn localization, exists. And furthermore, so we will give an explicit construction in a second. Furthermore, we will see from this construction that the functor from C to the localization is essentially surjective. So in some sense, you can really think of this localization as having the same objects of C, but somehow the localization, of course, does change the mapping spaces in general. It has to. If the mapping spaces will also stay the same, then you wouldn't have inverted anything. So how would we do that? Well, we need to universally invert these morphisms W. So here's a surprisingly silly way of doing that. We've seen previously that the functor from delta 1 to delta 0 is itself such a localization. So in other words, we've seen that delta 0 can be obtained from delta 1 by inverting the non-invertible morphism. And so something we could try in order to force all the morphisms from W in C to be equivalences is we take this functor from the disjoint union of W many copies of delta 1, which takes just each of these delta 1s to the corresponding morphism. And then we just take this push out, right? So we take this push out in, and now you have to be careful, you don't want to take this in just simplicial sets, of course. That's not going to be well behaved. But you have to take it in cut infinity, the infinity category of infinity categories, right? Thomas explained in the previous video that you can think of this as the homotopy coherent nerve of some simplicial enrichment on infinity categories. And so the claim is that if we map out of this diagram into any other infinity category D, right, then we get another square where we have C prime, D, and then here a product of, or let me write just a functor from the coproduct delta 1 to D, and then, oh sorry, delta 0, and then down here functors from coproduct of delta 1s to D. Right? We have this square, and the claim is this square is a pullback in cut infinity. And first instinct would be, well, didn't we define it that this holds, right? We took a push out. So if we take maps out, why isn't that a pullback? And that's almost true. But the problem is that mapping spaces in cut infinity are not given by these functor categories, right? These are not even Kahn complexes, they're infinity categories. So if you recall how we defined cut infinity, then mapping spaces in cut infinity were basically given by writing down the functor category and then passing to the maximal Kahn complex contained in that. So one way to think about this is that the functor category has morphisms given by arbitrary natural transformations. And then the actual mapping space, the maximal Kahn complex in here, that will only remember somehow invertible natural transformations. So it will be some sub-simplicial set, some sub-Kahn complex of this guy. And the universal property of pushouts a priori just gives us that the corresponding square of these subspaces is a pullback of Kahn complexes. Or rather, in the infinity category of spaces, sorry. And so we need to check something for the claim, but maybe let's first see why are we done if the claim holds. So the claim, or I state that somehow the C prime is already a localization of C at W. And how does this follow from our claim that this is a pullback? Well, remember that by the example we just did, this functor here is really fully faithful, and it gives me exactly the full subcategory on this guy on all functors which send these to equivalences. Right? So this exhibits this one as the full subcategory on these objects. So if you take the pullback, then it's a little lemma about pullbacks in cut infinity, then this will also be fully faithful, and it will have essential image exactly the sort of the pre-image of the essential image here. So this will consist of all the functors from C to D, which, after restricting, go to equivalences. But that means it's exactly the functors from C to D which send W to equivalences in D. And that's what we wanted to show, right? This pullback here exhibits this one as the full subcategory of this one on all the functors which send W to equivalences in D. So C prime is a localization. So what about this claim? Well, even a little more generally, it holds that for any push out in cut infinity, if we map out into any other category, so we need somehow for this argument we need way more letters than usual, but so if we go into another category E, then the claim is this is a pullback. And how do we check that? Well, we check whether some diagram in an infinity category is a pullback by taking mapping spaces, by mapping another object in and seeing whether we get a pullback diagram of spaces. So we check after taking map This is mapping spaces in cut infinity from yet another object, f, comma blank, right? So if this diagram here stays a pullback diagram in spaces after applying this for every f, then it's a pullback diagram in our infinity category. And that would show our claim. So how do we check that? Well, the crucial observation now is that map into a functor category is the same thing that we get if we map D into the functor category from F to E. And this shouldn't surprise you if you replace map by the full functor category for a second, right? So we just write fun everywhere, then this is sort of the usual exponential law. But both of these sides are also the same as just fun f cross c to e. Right? And these are really simplicial mapping spaces. So this is really just something that works for simplicial sets in general. But now, both this and that are by definition the maximal Kahn complex of these two things. Right? And this is really the same simplicial set. So these are actually the same simplicial set. I put equivalent here, but they're really isomorphic as simplicial set even. Right, so what does this tell us? Well, so we apply this map f comma blank to the thing up here, and then we can use this to put the f inside everywhere. And the diagram we get from that is map from D to fun f e and map from C to fun f e, etc. And now if you stare at this closely, this is really just mapping spaces out of our original diagram into the fixed infinity category fun f comma e. So this is actually a pullback. It's really just what we get out of the fact that this was a push out by mapping into this functor category f comma e. And so this might sound very abstract and maybe a little bit confusing, but basically what we've just shown is that push-outs in cut infinity are already satisfying this stronger universal property for the whole functor category and not just mapping spaces, right? So, and a fancy way of saying that is that cut infinity is actually an infinity 2 category. We will not discuss those in this course, but maybe if it's helpful for intuition of what's going on here, is that somehow here we don't just have mapping spaces, we have between any two objects a mapping category. And so you could phrase a priori different universal properties of pullbacks, either by just considering mapping categories as here, or just mapping spaces. And we've just shown that sort of the weaker version actually implies the other one. So this finishes our proof, as we've just seen previously, that the claim suffices to show that C prime is a localization. And so having this notion of localization in place, we can now finally define the derived category as an infinity category. Namely, we take our category K of A from earlier, and we take the subset of all morphisms which are quasi-isomorphisms. Meaning isomorphisms on homology. Maps of complexes which induce isomorphisms on homology, to be very precise. And then we let D of A simply be the Dwyer-Kahn localization of K of A at this set of morphisms. So that's a nice definition, but you'll notice that it's very inexplicit, right? So we've seen how to abstractly construct the localization as a push-out, but as a push-out in cut infinity. And so this doesn't tell you, for now, anything about how to think about mapping spaces in here, right? One can see from that formula that somehow the functor from K of A to D of A is essentially surjective, somehow something you can show about push-outs in stable infinity categories, that they in cut infinity. You can show that somehow they don't add objects. But so there's no new unexpected objects. You can still think of objects as being represented by actual chain complexes, but then mapping spaces are very inexplicit, right? And there are multiple explicit descriptions of how this looks like. In fact, from the push-out formula we gave, one can extract one, but it's not trivial to get a description of the mapping spaces out of that you can work with. So for example, one thing is this push-out in cut infinity, where we've pushed out along delta 1 to delta 0, or other co-products of that. One could compute that by replacing delta 0 here by some kind of blown up version, which has delta 1 sitting in there injectively, and then there's also morphism in the other direction, and everything is built in such a way that it's contractible, right? So you've somehow freely inverted the morphism. And then one could compute the push-out as the actual push-out and then fill all inner horns again, turn this into an infinity category again. But it's very unclear how to get at the mapping spaces from there. So that's something we will see in the next lecture. Thank you all for watching, and see you next time.